let me take you on a journey of exploration. The backstory begins a long time ago, billions of years ago, when a very simple life form on Earth, cyanobacteria, discovered something very clever. Now, I'm not sure about you, but I never thought of bacteria as clever, like that slime in your fridge or your compost. But this life form figured out how to harness energy from the environment. And in the process, gave off oxygen. That's photosynthetic bacteria. Well, oxygen, you may or may not know, but it actually poisoned most life forms around it. And eventually, over another billion or 2 years, ended up filling our atmosphere to 20% by volume with oxygen. So you all know, like, we all need oxygen to breathe. Without oxygen, we wouldn't survive. But oxygen is such a highly reactive gas, it wouldn't be in our atmosphere at 20% by volume or at any amount if we didn't have life on Earth. So that's kind of the point behind my talk. The whole goal in looking for life, signs of life on exoplanets, we're looking for gases that don't belong. But back to these stars and planets. You know, if there's an alien civilization, like intelligent beings, on a planet orbiting a nearby star, and they're looking back at Earth, they're going to suspect there's life here. And it's not with big things like the Great Wall of China or city lights or pollution, but it's from oxygen, a gas that's so reactive it shouldn't be in our atmosphere. So that's kind of what I want you to take away with you. We're looking to study atmospheres of exoplanets. We want to find gases that don't belong and signs of life on them. And I'm not here to tell you we found it. This is a long, long search. Like, it might be even a generations-long search. I don't want to disappoint you. But I am going to tell you where we're at right now. And I'm going to tell you exactly what we need to do to get there. So let's get started. How many of you have heard of transiting planets? Out of all those exoplanets out there, some of them are aligned just so they orbit their star in a way that from our viewpoint, we can see the planet go in front of the star, just like on this graph. But we don't spatially resolve stars, right? They're just points of light. So we don't see what's on the top cartoon. We see the bottom. We can measure the brightness of a star as a function of time. And if there's a planet going in front of it, the starlight will drop by a tiny amount. And after we're done, the star will go back to where it was. So that's great. But what I'm here to talk to you about is atmospheres. So do you see the cartoon on the top? You can see the planet in that dark part of the disk. And this artist has grossly exaggerated the atmosphere. See the atmosphere now? Okay. So if I want you to imagine for a moment observing this whole system at a wavelength where the atmosphere is fully transparent. We get a drop in brightness related to the dark part of that disk compared to the whole star. Okay? Now imagine we're observing at a wavelength where that atmosphere is very strongly absorbing. Now the planet's a tiny bit bigger. It's now as big as the dark part plus that gray atmosphere. So what's going to happen to this light curve? Is it going to be deeper? Or is it going to be a little shallower? Deeper. It's going to be deeper. We're trying to see if an atmosphere is there by looking at different wavelengths to see if that atmosphere is opaque at some wavelengths. Here we have data from the James Webb Space Telescope on a different exoplanet. We're now looking at the brightness of the star normalized to 1. So at 1, nothing's happening. This is a function of time. This whole transit lasts a couple hours. You see the very characteristic shape, right? It looks very box-like. The black is the best fit transit over all the wavelengths. But the colors are different wavelengths. Now this is a hot, puffy, giant planet. It's not a small planet where we can find signs of life. I'm just here to demonstrate for you it's a real thing now with probably, honestly, like at least 1,000 astronomers working in this field. And now I'm going to show you a more scientific version of that same plot, so you don't have to understand this to understand the rest of the talk. Now you're seeing amount of light blocked as a function of wavelength. So each of these points within a little error bar, that's one of those transit depths. So if we spent the entire hour on this exercise, you could literally measure how deep that drop in brightness is. Is it 1% or 2% or 2.05%, and make a little mark here on this plot. And you can see there's a certain wavelength where this planet looks a tiny bit bigger, right? Where it goes up. I know you can all see that. And in scientific terms, if this looked like a straight line, there would be no sign of an atmosphere. Because remember, we're trying to see where does the planet look a tiny bit bigger. It's around 4.3, 4.4 microns. And that's where this planet has carbon dioxide. So you know from Earth, carbon dioxide is a very strong absorber, right? It's a massive greenhouse gas for us, or massive, rather, very significant greenhouse gas. We only need a tiny amount. And so on this giant planet, there is carbon dioxide. It seems to show up on most exoplanets we've observed with the James Webb Space Telescope. And there's other gases, too. Here's now just a lot of ones. You don't need to know all the details here, but again, amount of light blocked is a function of wavelength. And look, there's a bunch of gases there marked out for you. So now there's this whole field of exoplanet atmospheres, and people are trying hard to piece together what it all means for a given planet. Is it what's going on with photochemistry, and can this tie into the planet interior and things like that? Earth is tiny, right, compared to our sun. So we cannot observe Earth's atmosphere with this method. Okay, we cannot, because our Earth's atmosphere is so tiny, it's like the skin of an onion on an onion. And that area of our Earth's atmosphere compared to the backdrop of our sun, or a Earth and a sun, it's like 1 part in a million. It's actually too hard. We cannot do it, okay? So that's in the future. The true Earth twin is in the future. Right now, we're studying what I call the Earth cousins, because there are these small stars that are 1/10 to 1/2 the size of our sun, and those are just cartoons. We don't spatially resolve any stars like that. But if you can just look at this picture for a moment, you can have this so-called sub-Neptune. Look, it's much bigger compared to its star than Earth is to our sun. And the one on the far right even more so. So our whole study with the James Webb Space Telescope, when it comes to small planets of the kind that might host life, we have to talk about not an Earth-Sun twin, but it's more like the Earth cousin, okay? I only wanted to convince you that we have a method to study exoplanet atmospheres today. So I think I've convinced you of that. A little problem with the star contamination, we're gonna get that. But imagine we have this now. What gases would we look for? Certainly, I told you about oxygen as a gas on our Earth. But what about other gases? You know, we have had oxygen, but only for about 1 billion years out of Earth's 4.5 billion year history has oxygen been substantial enough for an alien civilization to detect with the kind of telescopes we're trying to build. So I asked myself, what kind of gases could be produced by life on another world? Did you know life on Earth produces thousands of gases? It's not just that mold in your fridge, but you know, in the pine trees, they smell so good. That's isoprene, a biosignature gas. In fact, a little factoid for you is that every gas in our atmosphere that is there to the part per trillion level, with the exception of the noble gases, did you know that they are all produced by life? Even though they have a dominant source that is not life. So, wow, I used to not know much about chemistry, and any gas I could think of, I've listed some of them here, like ozone, supposedly is produced inside some cells. So again, there's just so many gases out there, and I and my team, we spent, I don't know, 10 or 15 years going through every possible molecule that could be in gas form. That might be a potential sign of life on another world.